In this lecture, we're going to talk about how to transparently communicate uncertainty. So the goal is to report measurements of physical properties in a way that anyone reading that measurement, if it's in a article that we're publishing or a lab report, or if we're just saying what it is or writing it out on a board, that anyone can clearly understand how precise of an instrument we used when we made that measurement. And so we're going to use something called significant figures. So significant figures are the number of digits that you report in a measurement. So remember, a measurement is a number and a unit. And so the digits are going to refer to the number of digits of the number. For example, if I had my previous example of 35 grams, right? So that's my measurement and I weighed something. I have 2 digits. So I have 2 significant figures in this number. So this would tell me in general how certain I was that the mass of the object I weighed really is 35. So the fewer significant figures I have, the less certain I am. And the more significant figures I have, the more certain I am. So something that would have greater certainty than 35 grams would be something, so this is greater certainty, would be 35.0001 grams. This has more digits that are significant figures as 1, 2, 3, 4, 5, 6. So this has 6 sig figs. So this is using a device that measures mass all the way out to the 0.0001 gram. That's really impressive. Something that would have less significant figures is if I had a measuring device that would report the same object that weighs 35 grams really weighed 30 grams. So here I have just one significant figure. And so I have something that is just not as accurate at weighing. When reporting a number, all of the measured numbers, all the numbers that make up the measurement are going to be reported as significant figures, plus one estimated digit. So in the case of this 35 grams, it would mean that the 3 is the digit that we were able to read a number on. So this is the part where we were actually able to read maybe a marking or read out. And then the 5 is our estimated digit. And so this means that really it's not necessarily 35 grams. It's definitely 30 grams at least, and it's less than 40, but it's somewhere in between them. So maybe it's like 31 to 39 grams. And we're estimating in the number that it's the 5 and not 36 or 33. So let's walk through another example of that. So here I have graduated cylinder. This is a way of measuring volume. And my units right here are milliliters. So I know my unit of measurement for this physical property. And I've blown up the area that's where the volume of liquid stops. I'm going to try to read that. So I'm going to report a number here. So it looks like the volume of the liquid is greater than 9. And it's less than 10. And I'm just looking here at the position of, not there, position of the liquid right there. And so I can now use the little markings. And so I've now used these kind of 2 big markings that have numbers. Each of these little ones in between represent, if the 9 is 9 milliliters and the 10 is 10 milliliters, each of those little markings is Sorry about that. Each of the little markings are 0.1 milliliter. So I can see that I've got at least 9.1, but it looks like it is probably right at 9.2. It's definitely below 9.3. So I think that, so we're going to measure from the bottom of the meniscus. There's a slight curve. I think it's just below 9.2. So that means that I can read 9.1 at least, right? Using those markings. Now I'm going to estimate one digit. So this is the part I can actually read. So now I need an estimated digit. And I think it's right in between that 9.1 and the 9.2. So I'm going to say 9.15 and split the difference. But I'm pretty much guessing on that. Like I'm just using my ability to look at that line and estimate. So that's my estimated digit. So it's 9.15 milliliters is going to be the measurement that I would report with correct significant figures. And looking at this has 3 significant figures because I have 1, 2, 3 digits in the number that I'm reporting. Let's look at a second example here. So let's measure something and say the first way we measure it with one device, we get a measurement that's 150 grams. So we know just by reading this number that it's going to be more than 100 and less than 200 grams. So we have this range of 100 to 200 grams. And that is that known piece right there. And then that estimated digit is the 5. So if it's 150, then we probably have markings on this device that are, if it's a scale, or if it is a digital scale, then we're going to see something where it's able to read at 100 and 200. And this is showing up somewhere in between for our reading. And that's how we're able to estimate the 150. So whoever made this measurement with whatever device, it was going to be accurate to the 100 to 200 range, and then that estimated digits coming in between. If instead we had 150.01, we would definitely know that it was more likely, we'd be more certain that it was 150 grams rather than 160, right? Because here, my estimated digit, sorry about this, it keeps jumping around. My estimated digit is the 0.01. So that means I know for sure it's 150.0, but it might be as much as 150.09, right? So I have this range, and it means that then there are markings. There's a 150.0 mark and a 150.1 marking, and this is probably going to come in around here, and someone estimated that it was 150.01. So it's going to be closer to the 150.0 than it would be the 150.1. And so just looking at these two numbers of weighing something, we could say that the 150.01 device that was used to weigh the mass of the object is going to be way more precise than the one that would report the 150 grams. So this is why it's important when you're recording numbers in lab or in an experiment that you are accurately recording the number of digits for whatever instrument you're using, because that you're not just capturing information about the actual mass of something, but also you're capturing information about the device used to measure the mass. And it's like, these are just numbers that are being reported, and it turns out there's so much more information held in that number than it looks like on the surface. So to summarize here, when reporting a measurement with correct significant figures, you're going to want to always report all of the numbers you can read to the nearest marking and then add one estimated digit. And so this is usually the amount between markings. If it's right on the mark, then your digit that you're estimating is 0. Now, if you're reading a digital device, let's say it's giving you a digital readout for mass or for volume or something like that, then you are going to report all of the numbers that you see in the digital readout. And the last one is estimated. So the device is going to do the estimation for you rather than the viewer of the measurement doing the estimation. So if I had a digital readout where it said 150.01 grams, I would just report all numbers. And I would know that this was the digit with the most uncertainty. I'm going to go over one last piece of information about significant figures that is challenging, and that is what to do about zeros, because zeros play two different roles in measurements and numbers. One, they can be a significant figure, they can be part of a measurement, but they can also be a placeholder that communicates the magnitude of the number, like its size, that it's a very small number or a very large number. And so we have a set of rules that kind of help us with when is a zero a significant figure that we would include as part of the measurement. So it's easiest when you don't have a zero at all. So if there's a non-zero number reported, you can just assume it's a significant figure. So something like 347 grams has 3 significant figures because there's 3 digits. So if there's zeros involved, there are a couple cases where they are going to be significant figures. The first is when they're between 2 non-zero numbers. So, for example, if our number was 307 grams, then the zeros in between 2 non-zero numbers. And so this is 3 significant figures. Also, if it's at the end of a number with a decimal place, the decimal place means that typically the digits that follow were ones that were actually measured rather than ones that are just a placeholder for us, the size of the number. So let's say it was, 3.470. In this case, because this 0 comes after a non-zero number and there's a decimal involved, it's a significant figure. It was part of the measurement, and it tells us something about the precision of the device. So this one right here is 4 significant figures. Now, there are a few cases when, two specifically, when a significant figure is not going to be, or sorry, a 0 is not going to be a significant figure. So first, it's if it's at the beginning of a number. So then it's going to be a placeholder for the size of something. So in this one, we have these 3 zeros that come before any sort of non-zero number, the 3. These are really just kind of telling us, no, this is an itty bitty number, not that we've measured these zeros, just that the numbers that we're measuring are very small. So these are placeholders. So these communicate magnitude. And this number would have only 3 significant figures. So the opposite kind of way that it can communicate magnitude is for very large numbers. So let's say we had something that was 347 and then several zeros following it. In this case, these zeros are also communicating magnitude. And so this will be 3 significant figures. And this can be really confusing because it turns out then that the decimal place just makes all the difference in the world. If there's a decimal place anywhere in this number, then those zeros will become part of our measurement. But right now it's just saying, oh, no, this is just a really big number, and our device is capable of measuring very heavy things, but not to the granular level of detail where it can figure out 0.1 grams, but it can figure out 1,000 grams. So something just to talk through if you're actually looking at a number and finding yourself confused about whether or not a zero is actually something that was part of a measurement or just communicating the size of a number.